Okay, so hello and welcome back. So in this video we will do basically a similar type of problem to the previous video, and if you want to be more familiar with the problem, you can either watch the previous video, but I will try to familiarize you with the situation. So essentially what I have here is an NPN transistor. So, and in the previous video I have talked a little bit about what these transistors are and how they work and so on and so forth. If you need more information about them, you can basically you can watch the previous video. You will get enough information about many different types of things about these transistors. So we call this V of S, and let's say that your V of S is equal to 10 volts DC. And let's say that your R of B, this is your R of B, this is your R of C, and this is your transistor, and you want to turn it on. You want to turn on the transistor, meaning that you want the transistor to go into saturation, right? Now again, to understand these terms, as like for example turning on the transistor or basically saturation, for that please watch the previous video to understand them properly. So again, over here, let's say that R of C, I mean to tell briefly about this, when you turn on the transistor, essentially the transistor acts as a closed mechanical switch, meaning that basically the voltage drop across the collector emitter junction of the transistor becomes zero, or very, very close to zero. And since the voltage drop across the collector emitter becomes zero, we say that it has turned on, or it has basically entered saturation, meaning that it's acting like a closed mechanical switch, right? So we want to, and we want to essentially do that here. So the collector resistor that we have here is 22 kilo ohm, and the beta of this transistor is equal to 75, right? So now the supply voltage that comes here is 10 volts, and this 10 volts goes through this resistor and goes through the PN junction and then goes to the ground. So what happens here is that if you want the voltage drop across this PN junction to be zero, that means that the whole supply voltage has to be dropped across this resistor. So I apply the Ohm's law, V is equal to IR to this transistor, to this resistor R of C, and so I want the voltage drop to be basically 10 volts here, right? And I don't know how much current I need for that, so I write I over here times R, which is basically the same resistor over here, which is 22 kilo ohm, which is 22 into 10 raised to the power 30 ohm, right? So that means that I is the same thing as 10 volts divided by 22 into 10 raised to the power 30 ohm, which is the same thing as for 10 divided by 22 is the same, or 1 divided by 22 is the same thing as 1 divided by 22 is the same thing as 0.045. I'm going to take that as 0.045. Take only two significant figures. So I'm going to simplify these 10 raised to the power 2. I'm going 1 divided by 22 is 0.045, and this comes to the numerator. This becomes 10 raised to the power negative 2, and the unit becomes amps, of course. course. Volt divided by ohms is amps. So that means that you need this kind of this current to be flowing through this call it I of C. You need your I of C to be equal to 0.045 into 10 raised to the power negative 2 amps, so that the whole voltage, so that the whole supply voltage is dropped across the resistor, so that no voltage is dropped across the PN junction, and that basically that is, and then in that case basically the transistor is set to be turned on, right? So how do I do that? And so of course I know the current that is supposed to be flowing here, and you know that in the case of an NPN transistor, I of C to I of B, and I of B is basically this current going through this branch over here. I of C to I of B is the same thing as is a ratio called the beta of your transistor, the gain factor of your transistor, which is equal to 75 here. So which means that now I know what my I of C is supposed to be, so I write 0.045 into 10 raised to the power negative 2 amps divided by I of B, that is supposed to be equal to 75. And so now this basically tells me that the current going through the base resistor is supposed to be this value divided by 75, of course, right? So that means that, and if you cross multiply here, you will get the same thing, meaning that you can say I of B times 75 is the same thing as 0.045 into 10 raised to the power negative 2 amps, and that means that I of B is equal to 0.045 into 10 raised to the power negative 2 amps divided by 75, right? So basically this whole business of beta, that means that basically your beta, whatever the value of your beta is, the collector current is always beta times the base current, meaning that if you rearrange this equation, it gives you I of C is equal to beta times I of B, right? So the collector current is always beta times the base current, meaning that when you know that your collector current is, for example, meaning that when you know that your collector current is this value over here, then your base current is going to be the same value divided by beta, which is 75 in this case. Now let's divide by 75. That gives me 0.000606. So I'm going to basically these two numbers divided by one another, that gives me 0.00061 606. Into 10 raised to the power negative 2 amp, basically amps, right? So that's the same thing as, I can write this as basically 6.1 into 10 raised to the power negative 4 into 10 raised to the power negative 6, into 10 raised to the power negative 2, into 10 raised to the power negative 2 amps, which is the same thing as 6.1 into 10 raised to the power negative 6 amps, which is the same thing as 6.1 microamps, right? So that means that your base current is supposed to be 6.1 microamps. So over here, I of B is supposed to be 6.1 microamps. So that's the whole story. Now, how do we do that? So you can essentially control your base current by making changes to this resistor over here. And the way that you can do that is that, of course, you know that there is a supply voltage of 10 volts on top of this resistor, and it goes on the other side, goes to ground, right? And this PN junction over here is not important because there is a 0.7 volt voltage drop over here across the base emitter junction. But since your supply voltage is 10 volts, it's not important. You can just simply ignore that. And so you can imagine that there is this resistor over here, that one leg of the resistor is connected to the positive rate, the other leg is connected to the negative rate, and so you want this current to be flowing through the resistor. And so, depending on the value of the resistor that you choose, basically some current is going to be flowing through your resistor. Now, if I apply the Ohm's law to this resistor V is equal to IR, then basically the voltage drop, the voltage on the resistor, I take it as 10 volts. That's the current is 6.1 into 10 raised to the power negative 6 amps times R, right? And then this tells me that R is the same thing as 10 volts divided by 6.1 into 10 raised to the power negative 6 amps, which is the same thing as, so this goes to the numerator, this becomes 10 raised to the power 6, and these two simplified, this becomes 10 raised to the power 7, and 1 divided by 6.1, I wish there was a way to know what these numbers would be. So 1 divided by 6.1 is the same thing as 0.1639. So I take it as 0.16. So take this as 1 divided by 6.1. I take it as 0.16 into 10 raised to the power 7. And the unit would be ohm, which is volt divided by amp is ohm. So that's the same thing as basically a 16 and 5 zeros. 1, 2, 3, 4, and 5. That's 1.6 megs, right? 1.6 mega ohm. I'm not sure if the value is correct. Let me see. That's correct. It's supposed to be 1.6 mega ohms. So you can see that. So that means that basically if R of B is chosen to be 1.6 mega ohms, then basically what happens is that if you choose this resistor to be 1.6 mega ohms, then this current becomes basically 6.1 microamps, and as a result of that, the collector current becomes 0.045 into 10 raised to the power negative 2 amps, and as a result of that, the whole supply voltage will be dropped across this resistor, which you can think of as load as well, This could be your load, for example, and that means that basically, since the whole voltage is dropped across this resistor, there is no voltage left to be dropped across this PN junction, and that means that the transistor is in saturation or is essentially turned on. So that means that when you want the transistor to go into saturation, you have to actually drive it with current. You have to essentially give it enough current so that and essentially that current is controlled by this resistor, meaning that you can basically connect, instead of this resistor, you can essentially connect a potentiometer and turn that potentiometer, basically decrease the value or increase the value in such a way that basically, and then you can put a voltmeter across this PN junction over here, and then watch this voltage as this voltage gets closer and closer to zero. Once the voltage is very close to zero, that means that your transistor is turned on essentially, and then basically you don't really need to do much calculation, I mean, really. But then you need to watch basically, you need to watch a couple of things, meaning that, for example, you need to watch your potentiometer, meaning that I have actually done this before, and you could actually damage your potentiometers, and potentiometers, it seems that they are pretty pricey, meaning that you have to pay $4 or $5 for a potentiometer. Or sometimes you could make some damages to your I don't know. For example, I did some in a couple of instances. I happened to basically to damage the fuse on my amp meter, meaning that the current went above, for example, 600 milliamps or so, and then I had to pay, and the amp meter, there is a fuse on there. You have to change the fuse, and then the fuse is going to cost you like $4 or $5 to replace the fuse. So essentially, you have to be careful a little bit with what you do, but essentially with experimentation also you can do the same thing, and so, but this is the way that you can calculate it. So that's basically that. Now we have a couple more questions related to these transistors. We will go through them as well. I'll see you in the next video. Thank you.